Well, I have to admit it's nice being the last panel because after this we all get to go home. And for those of us on the organizing committee, we've been on this for a while. So I'd also like to offer special thanks to James Boudelier from Navita for assisting with today's panel. Unfortunately, James wasn't able to be here this afternoon due to a conflict. So for me, any discussion of audio can't ignore the room. Apart from listening on headphones, we all experience audio in a room. And of course, those rooms have an effect, that is, transform the sound from an audio system. Hence, we can't ignore the room in the design of any sound system, be it a recording studio, a broadcast control room, concert hall, or house of worship. So each of the presenters on the panel will be giving a brief talk, and then after all these short presentations, we'll open it up for questions. I'll just introduce the panelists. I believe I first met John O'Keefe back in 1994 when I was doing my MSc at Waterloo. I was attending the Canadian Acoustical Association's conference in Ottawa to give a paper on my thesis work. John and I later worked on the Aga Khan Museum in the last decade. In this case, the room being a small theater with variable acoustics. John's team were obviously designing the acoustics, and Engineering Harmonics, the company I work for, we're doing the sound system. I've actually not worked with Terry Medvedik, but I do remember the first time I met him, which I think was on a phone call. It was in that awkward phase, post-graduation, pre-employment, and I had sent out a lot of resumes, just hoping to make contact with industry people. And I do believe Terry called me, and somehow the conversation got onto accelerometers, and he asked me if I had one. And if he had seen me, I would have had a blank stare, trying to figure out what an accelerometer was. I now know what an accelerometer is, but I still don't have one. But I did check at lunchtime, and apparently there are at least 10 free ones that you can get for your iPhone as an app. So I think we've solved that problem. I've known Arthur Scudra for many years. We've only worked indirectly together. Arthur's expertise with measuring sound systems in rooms is very well known. Perhaps some of you have taken training from him from SMART, and obviously he's a user of that platform. And I know that one of the projects where we were the compliance consultants, he was measuring that stadium. It was the redevelopment of Ivor Stadium, which of course turned into Tim Hortons Field, which incidentally is where I first met Dave Clark when I started at Engineering Harmonics. This would have been the summer of 1995. Ivor Stadium at the time was undergoing a replacement of their sound system. That was really my first foray into professional sound system design. In this case, the room was basically outdoors. Dave and I later worked on a new sound system for the Sky Dome, now the Rogers Center, and I spent, many hours tweaking that design through, and I'm not kidding, the DOS version of Ease. This is back in the Windows 3.1 days, so you were not running Ease under Windows 3.1. In fact, the model was so big, we had to split it in half and basically assume that symmetry would allow us to do the calculations on the other half of the room. Otherwise, the poor computer would still be analyzing. I've also known John Swallow for, I think, almost my entire time at Engineering Harmonics. John and I have worked on a few projects, in particular the Citadel High School in Halifax. So similarly to the Aga Khan Museum, this has involved a theater space. Again, you see that sort of that constant thread of acoustics and sound systems. They really do go hand in hand. So I'd like to ask John O'Keefe to come up and give us our first presentation.
I
think you might have to hit play.
was, hold on, how do we get this going? Oh, that's mine. There we go. All right, sorry, I was standing back there talking to John, and oh, am I on? You've seen this fellow before. Wallace Clement Sabine created almost single-handedly a new branch of science at the beginning of the last century, that of room acoustics. And like so many other developments in acoustics, or any other study for that matter, our discussion and conception of reverberation remains trapped in the technology of its infancy. Sabine quantified reverberation time with the tools he had at hand. In this case, a stopwatch and some organ pipes. So he could accurately measure an RT of about 1 or 2 seconds, but not much shorter. Now, in a concert hall, it takes about 2 seconds to decay 60 decibels. So the 60 dB range became our dynamic range for measuring reverberation time. That's the standard. Problem was, that's not how we humans perceive reverberance. Musical notes and speech phonemes are typically separated by fractions of seconds, not by seconds. In the mid-1960s, this man, Manfred Schroeder, His Teutonic Majesty, and a couple of his students found that our perception of reverberance correlates much better with the first 160 milliseconds of the decay. And when you think of how much separation we have between phonemes or between musical notes, fractions of a second do make sense. In 1970, so that, what's 160 milliseconds? Well, in a 1 second reverberation time room, a lecture room, or effectively this room right now, that's about 10 dB. So in 1970, Wilhelm Jordan proposed what he called then, and we still call today, the early decay time, which measures the first 10 dB of decay, and then we multiply it by 6 to get Sabine's range of 60 dB. Wilhelm Jordan was the fellow who designed the acoustics of Sydney Opera House, and there's a Toronto connection. His son, Nels Jordan, was the acoustician on Glenn Gould's studio. So there we go, small world. So although we typically only perceive the first 10 dB of decay, we still talk about something in a 60 dB range, which is a little bit strange when you think about it, and I'll talk more about that later if we have time. The next major development in room acoustics started in the 1940s and the early 50s. This was the beginning of the uncovering of what the great Lothar Kramer called the fine structure of reverberation. Now, you've all seen one of these, an impulse response function. A new concept of sound was developed, the so-called early useful energy and the late or detrimental energy. And different sounds, different types of sounds have different thresholds between the useful and the detrimental. For speech, that's generally taken to be around 50 milliseconds. And that came out of a 1950 landmark paper, which is all rather interesting. It was in the very first issue of Acoustics' premier scientific journal, Acoustica, and it is one of the few papers that is seminal both in the world of natural acoustics, my world, and the world of reproduced sound. In impoverished post-war Germany, this was late 40s, early 50s, the fellow who wrote this paper, Helmut Haas, didn't have an anechoic room to work in, so he used a hemianechoic room, the roof on top of his building. But what he came up with was really seminal. What he found in my world of natural acoustics is that sound arriving within the first 35 to 50 milliseconds will enhance speech intelligibility. And in the world of reproduced sound, he put numbers to the precedence effect, something, the term was first used by Kramer in 1948, but Haas put numbers to it, and some people call it the precedence effect. Most of us, I should think, call it the Haas effect. Well, this was pretty good, and in 1953, a fellow named Rolf Thiele came up with something that is used to this day. He put it to numbers, and if some of you have don't remember the squiggly lines from your mathematics, this is something called an early energy ratio. So what we're doing is integrating the first 50 milliseconds in the numerator to the total energy, so-called a simple ratio of early sound to the total sound. This is something he called Deutlichkeit. The English translation that we use is distinctness, something that I always thought was a bit unfortunate because it was meant to quantify speech intelligibility, something it does very well, by the way, much better than a reverberation time ever will. If you ever want to use a reverberation time for speech intelligibility, you can, well, it's a bit like the dinosaurs, isn't it? You'll be extinct soon. Now, there's one thing to notice about this D50 ratio, the integral, and that it's a step function. And by that I mean a reflection that arrives at 49 milliseconds is thought to be a good one. And if that reflection arrives at 51 milliseconds, it's a bad one. And of course, our hearing does not behave like a step function. Rather, there is a gradual progression for what is good and what is bad. And this was quantified by Lochner and Berger with a series of curves closer to what our hearing is. And they proposed the so-called Lochner-Berger ratio. That's something they could measure in their lab in South Africa in 1960, but no one else could, at least not with an instrument one could carry around with you. Thus again, the technology of a bygone era, an early 1950s, dictates our discussion today, even though we have much better tools to measure with. Different sounds have different thresholds between good and bad energy. For music, a fellow named Walter Reichhardt in the mid-60s came up with an 80 millisecond threshold. Music is actually a bit slower than speech. And once again, it's a step function approximation, but this time, unlike speech, for some reason, it's a logarithmic ratio. And once again, in the 1980s, my friend Eckhard Kahle came up with a better correlation at C50, at IRCAM, by the way. I don't know where that fellow went, but anyway. But acoustics discussions, it turns out, are a bit like our arguably dysfunctional election system. First past the post wins. C50 is more accurate. No one uses it. Now, by the middle 60s, the temporal aspects of reflected sound had been reasonably well defined. Then, in 1967, this fellow, Harold Marshall, opened up a whole new can of worms, and that is the spatial aspects of reflected sound. In a very short paper, it was called a note, actually, in the Journal of Sound and Vibration Research, Harold suggested that, hold on, a lot of our favorite concert halls are narrow. Could reflections arriving from the sides be important? Now, that sounds dead simple, and perhaps even obvious in hindsight, but that's true of so many of science's profound ideas. E equals mc squared is dead simple too, but it was hardly obvious before Einstein dreamt it up. Now, Harold's idea was taken up by a young student, Mike Barron, who did his PhD on it. That's Mike on the right there, looking a little older. And what he found was that if a reflection arrives at the listener from the side within the first 80 milliseconds, a perception of what he called spatial impression will be created. And in the mid-1990s, up in Ottawa, our friends John Bradley and Gilbert Salodra, I'm sure you know both those names, refined that definition into its early and late components. So reflections that arrive within the from the side within the first 80 milliseconds will create a sense of what's called source broadening. So that single violin on stage at the front of the room can appear visually, if you close your eyes and visualize it, it can appear to fill the whole stage in front of you. And if after 80 milliseconds, if the late arriving reflections are still coming at you from the sides, you will get a perception of what's called envelopment. And that's where the music surrounds you completely. It's almost as if you're floating in a cloud of music. It's a truly wonderful experience. Once again, at least for me, I find the technology of the day very interesting to consider. This is Mike looking much younger and with more hair, doing his PhD work. Digital delays were not available in Southampton in 1970, and hardly anywhere else for that matter. So he went down to his local music store and rounded up that pinnacle of contemporary acoustic scientific instrumentation. He got an Echoplex tape delay machine. He was doing what scientists so often do, employing what we now consider to be simple tools to develop very profound ideas. Haas had his rooftop anechoic room. Mike had his lateral energy Echoplex. And like Haas's work, Harold and Mike's work would go on to shape the geometry of auditoria. In Haas's case, it led to the overhead reflectors that started to appear in auditoria in the 50s and are still with us today. In Harold and Mike's case, it meant a return to the shoebox-shaped geometry for concert halls. You saw so many of them in the 80s, 90s, and even to this date. And then more exotic geometry, such as the vineyard step concept and the directed energy halls. First, we'll look at the vineyard step concept. Both of these geometries, by the way, provide sound from the sides. Um, you'll see the original on the left, that's Berlin, 1962. And on the right, a later version, which our friends at Engineering Harmonics worked on, the Walt Disney Hall in Los Angeles. And on the bottom, we see the so-called directed energy rooms. The very first, Christchurch Town Hall, 1972, and its latest incarnation, La Philharmonie in Paris. And one of the things that I find, I'm quite interested in evolution these days. I'm interested in the evolution of concert halls. Now, few would see the visual difference between the two rooms at the top. They're both vineyard step rooms. Both, and every subsequent one, I'm just about to go see the new room in Hamburg, which is vineyard step. They're all based on that 1962 Berlin Philharmonie. Likewise, not only do these upper halls share the same genus, these two on the bottom actually share the same acoustician. But if you look at the left and the right, they don't look all that similar at all. But the same acoustic principles are behind them. The other part of evolution is perhaps what one might call an old lateral energy warhorse. That is the shoebox-shaped room. You look at these two rooms and you think, okay, well, Lucerne is really just a modern architectural expression of the classic Musikvereinssaal in Vienna. The room in Lucerne, however, is an improvement on two very important levels. One, it is quieter, much quieter, and I'll draw your attention to the clerestory windows in Musikvereinssaal, which fortunately for me were open when I took that photograph. Lucerne is quiet down to the threshold of hearing, so-called N1. Now, I have yet to see a scientific study correlating the appreciation of concert hall acoustics with the ambient noise level. But the experience of sitting in a room like Lucerne or other rooms and having an actor or a musician hold 1,000 people or more on the edge of their seats in absolute silence, something we can't do here. It's hard to describe. You really are participating in a communal music experience. The other thing that Lucerne has that Vienna doesn't is Lucerne has very highly adjustable acoustics. And all those classic recordings of the Vienna Philharmonic are not done in this mecca of concert halls, Vereinssaal. That's because it does not have adjustable acoustics and is far too reverberant in its unoccupied space. Finally, we'll talk about sound level and loudness. If there's one thing we've learned about sound in a room is, at least for performing arts, is that our perception, much like any other perception, is a multidimensional experience. So spatial impression, clarity, warmth, and yes, reverberance, all need to be in their right ranges for us to have a good experience of sound in a room. The idea of an ideal reverberation time is thankfully, blissfully far behind us. But some people still think that sound in a room is still all about reverberation time. And for those, I say, well, go home and look at the biggest knob on your stereo. It's the volume knob. It's the one that controls loudness. It's not the reverberation time button. That is hard to get across to so many people. Up until the 1970s, no one really considered loudness in a concert hall to be important, partly because, and I don't have time to explain this, so that's partly because the acoustic strength varies often more inside a concert hall than it does from one concert hall to the next. But in the mid-1970s, 3 independent studies, 2 in Germany, 1 in Britain, all pointed towards the importance of loudness. The British one was carried out by Mike Barron, and I was fortunate enough to play a very small part of it near the end. In all 3 studies, they found out that the measurements did not correlate very well with the predictions. Mike got his pen out and developed something that we now call revised theory. In standard theory, as we all know, there are 2 components to the sound. The direct sound, which attenuates with distance, and the reverberant field, which does not, supposedly. The strength of the reverberant field in standard theory is assumed to be uniform throughout the room. Well, it's not. It turns out that the reverberant field attenuates at a rate of about 0.1 to 0.2 dB per meter. Is that a big deal? Yes, it is. If you're at the back of, say, a 30-meter long room, and you have a 0.2 dB per meter attenuation, that means you have to double the size of the orchestra on stage to hear things as loud as you do as at the front. This is how we quantify acoustic strength in a hall. That is how loud the natural acoustics are. It's a simple logarithmic ratio of the reflected sound, which we see in the numerator, to a agreed to reference level in the denominator. And that reference is taken to be the free field or anechoic level at 10 meters. 10 dB is only chosen because it's convenient if you're quantifying things in base 10 logarithms. And this is how we predict strength using revised theory. And I'm showing this to some of you because you may not have seen it before, and you can look it up on the internet. Just type in revised theory. And like standard theory, we have 2 components. The direct field, in this case, it's referenced to a free field, or anechoic, at 10 meters, and the reverberant field, but in this case, it attenuates with distance. These are some measurements in a room I designed about 10 years ago, I guess now. And I'm measuring acoustic strength, G. We call it G because the Germans thought it up. And that's what standard theory, that's the strength, acoustic strength in the room that standard theory would predict. This is what revised theory predicts, and you can see a much better correlation. And here you're seeing the just noticeable difference for acoustic strength in a concert hall. It's about 1 dB. And as I say, you can see a much better correlation between revised theory and the measurements compared to standard theory. So not only do we have a much better correlation, those just noticeable, the JNDs tell us that it's a subjectively significant difference. We're more than 2 or 3 JNDs there. I mentioned briefly our misplace concentration on reverberation time, and the same is true for sound system design. Gain before feedback. Think about it. Gain before feedback is not governed by reverberation, at least not directly. It is governed by how loud the room is, and that is determined by acoustic strength, G. So now we have two ways of calculating the level of strength in a room, standard and revised theories. Which one should we use? Well, if you're in a control room or a studio, standard theory is probably just fine. But if you're working in a room that where you're going to have listeners, say 10 meters away or further, an arena, for example, you're going to want to use revised theory. Now, of all the parameters that I've mentioned, this G is the one, as I said, corresponds with the biggest knob on your stereo. But it is the one that's had the hardest time catching on. Some of you may not have heard of it before. That's because it's very hard to measure. And I paraphrase Churchill, there are lies, damned lies, and reported measurements of acoustic strength. And in my final bash at how we quantify sound in the 21st century, think of the parameter that we use every day to quantify how loud a sound is, dBA, or in some cases, dBc. Now, dBA is a single line approximation of the equal loudness family of curves, something that an analog filter could do when it was first introduced some 70, 80 years ago. Now, a dBA filter is simply an inverse filter of the loudness curve somewhere around there, around 50, 60, in that range. dBc is for sounds a little bit louder, and it's, oops, went the wrong way. And it's somewhere up around there. These days, the whole family of curves could be calculated on your smartphone. But don't expect a conversation in phones to replace a conversation in dBA anytime soon, because it ain't gonna happen. First past the post. Since I was a kid, I found this stuff fascinating. I mean, we all do. All of these wonderful discoveries that I've told you about, many of them were dreamt up by people who are still alive to tell the story today. Some of them are my friends. When people ask me, how can you quantify something so sublime as concert hall sound? How can you do that in numbers and graph? Well, my response is, you can't, of course. But we do need a vocabulary. We do need cold, hard facts when we're trying to make multi-million-dollar decisions. Airy-fairy opinions won't cut it then. These numbers and the graphs and the formulae that I've been telling you about are to acoustics what notation is to music. Sure, it doesn't tell the whole story, but it is an indispensable form of communication. Without it, Palestrina, Bach, Beethoven would, and well, too many to mention, would probably be lost to us forever. Think about it. Think what it must have been like to live in the times of the monks when they were developing musical notation. That's how I live my life. It's a lot of fun. A few years ago, John Bradley and I organized something called the International Sound Symposium on Room Acoustics, ISRA. 160 of the world's best acousticians came here to Toronto. And the night before the conference, I had 50 of them in my backyard. It was one of the proudest moments of my life. Thank you very much for your time.
Thank you, John. Okay. Up next, we have Terry Medwedick.
Go get him, Dare.
Yours?
Yeah.
There you go.
How did I do? Does this clicker work?
Oh.
Yes. Does this work? No?
I don't know.
We didn't try it.
Okay. So I'd like to keep this short and sweet. There's a lot of things that everybody knows already. Many of you have been in studios. A number of you are studio owners, and you've experienced the joys of relocating or building a new facility. And the reason I'm bringing this up is in the past 3 years, I've witnessed, well, actually 3 facilities relocate, and in haste, they signed rather lengthy leases, and on 2 of them, the leases they signed were to environments that did not suit their purpose at all. They found out that the floor wasn't strong enough to support the weight of even lightweight post rooms. Mechanicals didn't run properly. So I'd like to just go over general studio considerations, design considerations. When contemplating a relocation or a build, it's very helpful to have the staff get together to go through a list of the things that you require. Now, there's going to be a wish list, and then there's going to be what you can get away with list, like a need list. And so it'll be comprised of the rooms that you require, whether a single dedicated room is going to be fine, or whether you want that single room to serve multi-purposes, which is quite popular now. The formats, the number of people that are going to be involved, the number of occupants, which often now drives the size of the room. And most importantly, well, in line is your budget, to be realistic about what the amount of money you can afford to spend based on your business plan. In searching for a building, it's a matter of whether you're looking for to build from the ground up, which is rare because it's quite costly. But if you're buying the land, it's quite good. Whether you're moving into an existing freestanding building or a condominium building of sorts, all these things have an impact. Now, this is not a comprehensive list. From these, there's other breakdown lists. So if you're doing something from the ground up versus moving to an existing building, there's 2 different branches of questions that go from there. You have to look at the proximity you are to streetcars, to trains, etc. These all have impact on the design of your facility and what ultimately you're going to end up paying, depending on your criteria. And again, how good you want it to be. Site location within the building, whether it's at grade, below grade, or upper floors. Structure of the building, concrete or wood. Dead loads are very important to know. So when you're speaking to your real estate agent, you give them a series of questions. One of them has to be, or should be at least, for the landlord to give some indication as to what that floor can support in dead load and in live load. A lot of the old wood frame buildings in the city originally were used for warehouses. They originally could design to, or could support 80 pounds a square foot, 100 pounds a square foot, but over the time, wood dries out, and now you're lucky if they could support 40 pounds a square foot. So here, for example, one of the minimums for a broadcast type construction would be 60 pounds a square foot of dead load in a building if you're looking at one. For post audio, anywhere from 100 to 300 pounds a square foot. I think the CBC buildings were designed to be between 250 and 400 pounds dead load. I think John would,
I'd have to
if John could
find
flash
out.
back to 1987. Mechanical. This is a big ticket item. Find out if the base building has a seasonal only system, whether it's cooling year round. And what's quite popular now in a lot of buildings across the city is the mechanicals are shut down between 6 p.m. and 7 in the morning. So if you are eager to sign your lease, make sure you find out how long that mechanical is running, because if you need the room at night, you're not going to have any airflow, then you have to either negotiate a deal with the landlords or you put in your own system, and that's not going to be cheap. Landlords, check the lease to see if they've included a noise and vibration standard. That will determine also how much noise or for you not to disturb the other tenants in the building, especially if you might be putting in a music studio, etc. Now that also applies to the tenants, so they don't bother you. Zoning, find out if it's zoned for broadcast or for recording, and whether it's a commercial, residential, or industrial space. Space plan development. In the initial stage, when you're working out the rooms that you require, if you were to calculate the interior sizes of the rooms, you don't have to work out the fine dimensions, but just the rough sizes. By net to gross, what I'm talking about is, because in audio the walls are thicker, typically anywhere from 6 inches to 14, 16, 18, 24 inches in thickness. That includes the acoustic treatment, much different than a commercial office space. That takes away a lot of square footage. So that's what I mean by gross or net to gross. So if you need a room that's 400 square feet, you might need 625 square feet to fit that in. So if you're negotiating for square footage in a building, always try to work out the outer dimensions of your room. Again, for site plans, your studio should be not located near the mechanical buildings, the mechanicals of the base building. Consider whether or not you're going to have any form of future expansion. What I'm also seeing now in some facilities, general offices are now becoming post-audio mix suites or edit rooms. So maybe in the back of your planning stage, you could think about that. The interior design, again, driven by the function, the number of occupants. The control room interiors, as many of you know, it's a much stricter form than in studios, because the control room is the reference room. You need to really know accurately what's going on. Appropriate wear surfaces, etc., is part of the design. Budget, it's really helpful to know up front, because in the initial stages, instead of spending months of time once you get the architects involved and everybody, and the budget is unveiled, it could be too late. So it's always nice to have an idea of what you can afford to spend in the beginning. Talk to your favored studio designer or architect or other consultant to get a knee-jerk reaction, at least, to see if that budget will work for you. And then you decide whether or not you have to downgrade, reduce your criteria, or just make it fit. Contingencies are typical things that sneak up on you from the landlord. Again, during construction costs can go up to 25–30%. If the landlord imposes a restriction on when you could load in and load out, or if they say in the initial framing stages of the room, you can only build at night. So all that has to be factored into your budget. Ventilation systems, again, on a room-by-room basis as to how much noise how quiet it's going to be. And when you talk to the mechanical system engineer, it's really important for them to understand, especially if not been involved in this, that the noise is not just the grills, it's the entire system, including all vibration. It also includes all the other HVAC systems in the building that might affect you. The cooling capacity, it's again important that they calculate the actual heat generated in the room relative to the heat loss. That is, if in a sound-rated room, you're very, very insulated compared to an office. So that heat is retained, and it has to be exhausted in a proper manner. A number of engineers might possibly overcool the system, and that's really quite a danger because then you get into short cycling. I think you've all experienced short cycling where the room freezes up, system shuts down, becomes beautifully quiet. 10 minutes later, it kicks back in with a thunder, and then everybody's cold again in 5 minutes. And that's something you'd like to avoid, is overcooling, and then it's over-design. You spent more money than you had to. The air velocity is very important. Oversized ducting in your planning. Just think of acoustic ducting being anywhere from 3 to 4 times the size of regular ducting maybe used for an office. Again, in your planning of the corridors, if you're thinking of plenums inside your studios. In general, create a critical list right up front with your staff, and again, maybe together with your favorite consultant or even before you get them on board, and just work out all the details, work out your business plan, the rooms that you require, maybe start doing some walking about the city, looking at locations and buildings, and then get the people, your consultants involved, and ideally, depending on the criteria, get the consultants involved prior to the architects. So at least the architects give them a full package of information that they can start working with. And then it's a matter of looking for the building. So all these things, there's no particular order to all this, but it's a matter of what you're looking to do. At the end, the news may be that you have to look at or accept certain compromises. Say you're downsizing and you're forced to move into a building that can't support the weight of your rooms, accept the fact you might have to monitor at lower levels, reduce your room size, do anything to fit the business plan, and maybe work more at night so you don't disturb the people downstairs. Again, these are compromises that I've seen as reality. And that's it.
Thank you, Terry. Arthur?
Okay, I'll try and be as quick as I can. I'm coming from a perspective of not only a consultant, but oftentimes I get called in to do combat audio. And what I mean by that is oftentimes I'll be given a basket of eggs and I need to make something out of it. So oftentimes contractors and consultants call me and say, you know, they're waving the white flag here. Can you come in here and rescue this project? And oftentimes I'm called in to fix a mess, and I do a lot of system commissioning. In fact, a good chunk of my business is just simply system commissioning and tuning of sound reinforcement systems. That's pretty much what I do most of the time right now. I do still have a couple of consulting clients that I get to do a lot of design work as well. But anyway, here we see a typical conference room that's thrown at me, and they say, okay, we want to do conferencing in here. How do we make it work? Well, I hate to break the news to you, but if it looks like a fishbowl, it's going to sound like a fishbowl. There's nothing I can do to wave my electronic magic wand to make that go away. So oftentimes I'm called in, and we need to look at treating the room somehow to reduce the reflective energy within that space. I mean, you know, for a room this size, you're really not dealing with reverberation more than you're dealing with reflective energy that's just way too much and very, very excessive. And, you know, when you try and get an echo canceller to work with this kind of environment, it's really very difficult, very challenging. And there's only a few DSP processors out there that I would trust to be able to handle this kind of nonsense. But ideally, you want to be in circumstances where you are in a much more friendly environment. And oftentimes, the architect really doesn't understand what is required for really good conferencing. You know, one major problem I encounter all the time is a high noise floor within the space. And oftentimes, what happens is a big corporation takes over an entire floor of a building, and the architect just designs away and doesn't think about the impact of the air handling system within a conference room environment. And when I tell them, you know, I want a noise floor here of, say, an NC 30 rating, I get the typical deer in front of the headlights look and go, okay, well, what do I do? You know, and it's like hire an acoustical consultant to come in here and design the air handling system to support this. But, you know, oftentimes that's always, you know, second fiddle to, you know, everything looks perfect here, or the client is on the 50th floor of the BMO building and he wants to see the lake and the pretty view that he's spending $1 million a year on. He wants to have that as part of the conference room. So it's really a never-ending battle that I'm dealing with. You know, another problem that I encountered many times is, you know, they design the entire floor with a noise masking system because it's following an open office concept. So they design the noise masking system to cover the entire floor, and they don't think that, hey, in a conference room, you don't want that noise masking system introducing noise into the equation here. So oftentimes I'll look up in the ceiling and see if there's some little noise masking speakers hiding in there, and I'll have them remove those from the conference room, and it just makes a world of difference. So another example, and I'm sure you guys can figure out what this one is here, but it's a typical council chamber, and this was one of those white flag waving contractor calls me in the last minute and says, I need to fix this problem. And what it started off with was a really simple job. You know, we're just replacing the DSP. We're just upgrading it to the current generation DSP. How hard can that be? And the problem was, you know, when I came into the site, I looked at the file and it was like there's no management of latency, because, you know, oftentimes we go in and commission a system and all we're worried about is EQ, 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 you know, making things sound nice and linear in response and everything like that. And oftentimes the timing component falls by the wayside. In this case, it was really a very challenging situation here in that I was given a acoustical set of parameters here that were really difficult to handle. If you look above, there is a very pretty ornate ceiling there that is actually a dome. And lo and behold, the focal point of that dome happens to be exactly where the podium is for the presenters to council. If you step right into that podium and you talk, you hear acoustic gain, no sound system required. It was really uncanny. But you know, when I divided this system up and said, okay, let's divide and conquer here and figure out how to make this sound system work, we had multiple sources that we had to deal with. So you could see I had 4 zones to work with here just with the delegate system. And on top of that, I had 2 line arrays on the sides. Then I had 3 zones within the PUBAC system where the audience sits. And then on top of that, I had some delay speakers in the round at the bottom there of some ceiling speakers to cover the back part of the room. So you can imagine all the different delay times. It was quite a massive undertaking. It took me about, I think, close to 16 hours to commission this. And I mean, it was just on a very last minute basis. And the 2 of us, we went through, and it was a very meticulous process to make sure the latency of the processor and the delay times that were required to make the system cooperate with each other. It was quite the challenge to make this work. It was quite a puzzle. And on top of that, you know, EQ as well. You know, you're dealing with a lot of concave surfaces in here. You're going to get some really interesting resonances happening. And no fault of the sound system or the acoustics, it's just what it was. And, you know, you're given this basket of eggs, make something of it. You know, and as I was going into the final stages of commissioning, I was going, I hear this 150 hertz resonance. Where the heck is it coming from? You know, the delegate system wasn't producing it. So I started, muting different parts of the system, and lo and behold, it was actually coming from the pewback system, and it was affecting what the mayor was hearing back in zone 1. So just a notch at 150 hertz in the pewback system cured a problem that was manifesting itself at the mayor's seat. So it was very, very interesting project that I did, that I took on, and we were pretty successful with it. I'm hoping to go back there and do a little bit more polishing, but it was a fun project. Finally, restaurants, it's a thing that I've been getting into lately with some of the projects that I've been doing. This is actually the dining room at the Cactus Club in Toronto. They've hired me on to be kind of their consultant and all that with all their newer restaurants and everything like that. Currently, I'm working on the new location at Sherway Gardens that's supposed to be opening up here in a couple weeks. But a very interesting situation here. We're dealing with an owner of the restaurant chain that not only has probably one of the most incredible palates for taste for food, he's very, very particular on things in the menu, and just a phenomenal guy. But on top of that, his sense of hearing is unusually keen. I was actually quite shocked at how he was able to hear things that normal human beings wouldn't even notice. And here he was going, there's something wrong in the low frequencies here. Can you fix it? And, I go in there and listen and analyze and notch things out and make things perfect for him. And so he's developed a good relationship with me and has trusted me with some pretty major projects here. But the cool thing here about this is reflective of what's happening at Sherway Gardens, is that we were able to put together a system here that marries both good acoustics as well as really excellent sound reinforcement systems here. That entire ceiling, it's a wood slat ceiling, and behind that wood slat ceiling is a lot of absorption up there. So if you want to have a wonderful environment to dine in and be able to have an actual conversation with someone, go to their dining room, which would be a little bit more sedate. Not only do we have a really good sound system in there, but acoustically it's treated to absorb a lot of the frequencies from people. So it's a pretty dead environment to begin with. We introduce some diffusion using the wood slats, and then we hide the speakers in between the slats to create a really nice ambient effect with the background music. Obviously, they also have a lounge, or what people refer to as the bar, and that's where things really rock. But even in those situations, I'm doing some really funky tuning with the equalization of that system, where I'm actually notching out the vocal frequencies of the music and suppressing them, so that quite literally it could be really rocking in the bar, but you could still have a conversation with someone across the table. And a lot of people don't think about that when they optimize and tune a restaurant, and this is something that they're very keen on. And when I'm actually tuning the system, I'm actually watching people and seeing what their response is. If they're actually having to lean in a little bit to listen to their neighbor, then I'm doing something wrong. So it's just a perfect example of the marriage of good sound and acoustics here. All right, so thank you so much.
Thank you, Arthur. Dave? Get you going here.
Hi, my name's Dave Clark. Today I want to talk about not the technical aspects so much, but the building environment, the process of getting some of these expensive buildings built in the construction environment. Arthur's been talking about, for instance, working closely with the owner, and that has its I'm sure, challenges, but also some advantages. A lot of big buildings are built with big amounts of capital money that are put in to the project, and the money is entrusted to project managers, construction managers, and I want to talk about the two different ways, or two of the different ways that this can be done, and how that affects the relationship between acoustician and sound system designer. I've worked with all three of the acousticians here, all four, and had great collegial relationships with them, but it's all been in the context of the first construction organization that I'm going to speak of. I've also had less collegial relationships with other acousticians in the second. The first one, I call it design, bid, construct. What this means is that the sound designer like myself will put together a bid spec, do the design, work with the acoustician. We make our plans, and the idea is that when we come out of it, the acoustics support the sound works well within the acoustics, and hopefully the building has a harmonious outcome. So in this structure, first of all, there's design, and timing is involved here too. So in the design, the architect works for the owner, the acoustics designer and the sound systems designer work for the architect often. They may work for the owner, but they have to fold their work into the architecture, and especially the acoustician has to do that. I won't speak completely for acousticians, but generally, the acoustical design is expressed through the architectural design. Their designs are coordinated and costed by the architect on the owner's behalf. And the owner still has a lot of input. But the budget gets massaged, the value of these improvements get folded into it, and eventually a cost estimate comes out of it. That part of the professional, or the expectation of a professional designer, is that the budget is accurate. Then this goes to bid. The general contractors bid on this package, and that includes the sound system design. And it may not, but I'm not going to, in this discussion, try to be too formulaic about it. I realize that there are variations on every job. I'm just trying to get the general sense of this across. The general contractor, as they say in America, buys the job. So they agree to build the documented design of the design team. And then there's construction. The general contractor works for the owner, the construction contractors, call them the trades, and the sound contractor work for the general contractor. Again, variations on the theme. So here's the structure. On the design team, we have the owner who has the authority, and these blue lines are basically authority, or let's say a reporting relationship. The owner is entrusting the architect to realize the vision. The architect is working with the acoustician and the sound designer to realize the owner's vision. The construct team, the owner has hired the general contractor, and the general contractor has hired the trades and the sound contractor. The relationship, therefore, when the job is being built, is that I've just taken the two sets of relationships, and then I've added the green lines, which are the architect is directing the work of the general contractor. Any massaging that has to be done comes from the architect to the general contractor. The acoustician is informing the construction techniques and may come in and look at specific situations during construction and give advice that is then enacted on the job. It might be a separation in a floating slab where it abuts a slab that's fixed. How's that being done? Noise transmission, all kinds of things come up. Similarly, in the sound design, things come up. The sound designer is making decisions, working with the sound contractor to realize the original goals. Then there's the flip side, which is the bid, design, construct, structure, and people call it design build. First of all, there's a bid. The general contractor agrees to build to the criteria of the owner. The owner says, I want a building. Like other buildings of this type, it's got to have these certain characteristics. Here's the land I bought. It's got to fit. Here's what it's got to do. Give me a price. The general contractors team includes construction trades and the sound contractor. So he's been phoning people and he's been saying to the electrical contractor, all right, here's the deal. You've done buildings like this. How much for the electrical? And similarly, he'll phone the sound contractor and he'll say, okay, we've worked together before. How much for the sound? Then they design once they've got the job. At this point, the architect is working for the general contractor. The acoustics designer is working for the architect. The sound system designer is working for the sound contractor. Sound contractor either has people in-house or he hires somebody from the outside world and says, okay, we got to do this. You got to help me get it into the budget and design this thing. Their designs are coordinated and costed by the general contractor. Then they construct. The trades and the sound contractor, in this case, work for the general contractor. So the design build team has a general contractor who's engaging an architect, who's engaging an acoustician. The general contractor engages the trades. The general contractor engages the sound contractor, who engages sound design. The lines of communication and authority are different here. It's basically straight from the general contractor to the acoustician via the architect, but in matters of acoustical expertise, the conversation has to be straight to the acoustician. Similarly, the general contractor is talking straight to the sound designer. Okay, what are we going to do about this problem? And then they have meetings. Here's an example. This is intelligibility in a natatorium. Now, I will preface this by saying that one of the criteria of the owner for this, a natatorium is the word I got from Terry, basically means a place where people swim and dive. This is a big room. The events are televised and they're international. One of the criteria of the owner, expressed by the owner's consultant who put together the criteria, was a laundry list that had to be met by the team. The system must provide a minimum STI of 0.5 throughout the space. And those are the words. Well, this is a very legitimate, well put together statement. It's clear. This has sound transmission index is a expression of intelligibility. And 0.5 is a value that was established in British standards, and acousticians can correct me if I'm wrong, eventually became an EU standard and is accepted throughout much of the international world. North America is a little bit special. So this is a requirement, especially for international participants. It has to do with evacuation under emergency conditions. It's a very sensible requirement throughout the space. Everybody has to hear it. You, me, all of you. It has to be equal everywhere, and so everybody can get out the door. So here we are now. The other discussion is about the tool. So how do you build a building that's never been built? How do you predict how that's going to work? Like, what's never been built? So we use predictive software. In this case, there's a very popular software called EASE. And in EASE, I've drawn the building here, put speakers in it. The speakers are good speakers that work well. They're not particularly expensive, but they are certainly stalwarts of this kind of work. They work well. They provide very acceptable results. what you're seeing in the picture, and it might be a little bit difficult to spot, but the long rectangle on the floor is the swimming pool for, you know, the long swimming events, and then the dive tank is down to the right, and then the stands are up on both sides, and you can see there are catwalks with the speakers mounted on them that cover all the stands, and they also cover the pool edge. So if you start out with the premise that you're going to have a low-cost building, you say, okay, we're going to have a steel ceiling, pretty much like a warehouse. Well, here we are. And this ceiling has been treated. If you do the measurements, you can see that the lowest value of intelligibility in that room, so this is a map of intelligibility in the room. So it's that same room. You can see the long swimming tank, the smaller dive tank, and the two sections of spectator stands on both sides. The low value is 0.34. It's unacceptable, really unacceptable. And the highest value you find is 0.53, and that's right in front of the speakers. Going back to the speakers, there they are. So if you're standing right under a speaker, it's pointed right at you, you will barely, I mean, that's the minimum standard. Those people will get out. They'll understand the message and leave appropriately. So this is an unacceptable solution. Well, now we have to add some cost. Okay, now we're going to consider two kinds of acoustic deck. One is 1.5 inches thick. An acoustic deck is another steel ceiling, but it's got ribs, and the ribs have holes in them, and the holes are stuffed with fuzz. So the sound goes into the holes, gets soaked up in the fuzz, and it's an acoustic absorber. So it reduces the reverberation and lowers it sufficiently that the speakers can do their job effectively. But again, the thickness of the deck and the amount of absorption there is a cost. It's a cost concern. So if you look at it first in the modeling system with 1.5 inch acoustic deck, you can see it's actually pretty good. The low value is 0.49 though. Well, the standard said it has to be 0.5 throughout. You don't go into a project like this saying, well, I was going to do most of it, but not all of it. You have to meet the criteria. So there you are. In the corners, those people will have a reduced intelligibility. I put the number up there just because the program will tell you, but that's 1,355 square meters of steel ceiling. That's a lot bigger than this room, for instance. And there's a significant cost difference between, you know, solution A and solution B. Solution B, you have a 2.5 inch acoustic deck. It's thicker, there's more stuff, it weighs more. Does it weigh more? Only a little bit, I guess. But you can see that its lowest value is 0.51. So in all, it's compliant. The previous solution is non-compliant, this is compliant. But then we have to remember, we're arguing about what a software program is showing us. In the end, do we believe that we're going to walk in the room with an intelligibility meter, a meter that can show STI, which you have to think about the tools of how they measure this thing. John was talking about the old A weight. The beauty of the old A weight is that it's a simple filter that could be built into a simple, you know, even Radio Shack makes one, although it's not rated for that kind of work. But if you have a properly calibrated meter with a simple filter in it, the noise control bylaw officer can walk around and actually take measurements. It's verifiable, it can meet simple legal standards, and so the same thing is desired with intelligibility. And those things now exist. So the conflict is, who's going to pay? Is the general contractor going to pay for thicker acoustic deck, or will a sound contractor have to buy more expensive speakers? And so this leads to meetings where you sit there at the table and the general contractor is pounding the table. He's not going to buy anything more expensive. And what do you really need all that stuff for? And do you believe the software? And then the sound system people are saying, you know, we contracted to meet the criteria, but it's not entirely dependent on our work. It's dependent on you spending some money. And we have done a reasonable design using reasonable products. It's not on us anymore. And so the acoustician and the sound system designer find themselves, instead of being in a collegial relationship, they're now in a confrontational relationship. They're both being pressured to change their design, to change their approach, to meet cost criteria. And I think that's the end of what I have to say.
Ramming up on 5 o'clock now,
Sorry, get me going here.
hopefully you can.
Pardon me, if you're wondering what's going on, while sitting up there, my leg went asleep and it's still not entirely awake. So if I'm limping, that's why. A little unusual. It has happened to me once before.
He was asleep at the time.
Okay. Yeah. Just forward?
Yeah,
Yeah, okay. Good.
probably should take about 15 because then we'll be only
Yes,
10 minutes
so
over.
we have 5 minutes left. Those of you who would like me to speak really, really fast, put your hands up. Okay, well, first, thank you very much, especially Terry for inviting me today. I'm
Yes, Terry.
delighted
Yes,
to
thank
speak to
you.
everyone. Funny, I usually start by asking if people can hear me and point out that acousticians do that kind of thing, and it usually gets a laugh. But of course, in this case, you're way beyond me with a mixer. Okay. So what I'd like to do is just do an example of the work that we do. So I'm a consulting engineer. The work that we do divides broadly into 3 areas: environmental noise issues, vibration of structures and buildings. In fact, CN Tower, when I saw it up there, brings back a lot of memories. We put 2 vibration dampers on CN Tower when it was built, and I was a student at the time, and I was part of the project and did a lot of the design work. It was an extremely exciting thing you can imagine. That's structures and vibrations, a lot of floor vibration, studio building vibration. And then the third is architectural acoustics. And broadly, within architectural acoustics, I'd say most of our problems relate to either speech intelligibility problems, where we're in a room and we're trying to add speech intelligibility, or music appreciation, which is the kind of subject that John O'Keefe was speaking about, okay? Or we're looking for speech privacy, or privacy issues, where we're trying to keep the sound from one room out of the adjacent spaces, the kind of thing that Terry and Dave Clark were speaking about. So, the difficulty in the kind of work that we do is that generally most of it has to be built and completed before we actually get to test it. So if we make mistakes, it's serious difficulty because oftentimes we're even occupied before we get a chance to test. The second thing about this subject field is that if there ever was a field where the devil's in the details, this is it. There are so many examples I could give, but in fact, mentioning CN Tower, we were just designing a device to absorb energy. It was 2 pieces of pipe and a little valve. Should be nothing to it. But by the time all the secondary problems were involved, there are 30 or 40 pieces of pipe, so many valves and things, we couldn't fit it in the available space, and it all had to be custom made into what hydraulic engineers call a valve body. Again, the original problem was one little thing, and it grew into 30 or 40 problems that had to be solved in order to make a device that works. And again, so that's what I call the secondary problems. Okay, around to this project, Crow's Theatre. Crow's Theatre, the theatre company, is a small theatre company in Toronto. They've had about 20-year history, been very successful. A fellow named Chris Abraham is the creative director. He's a very creative person, a great person to work with. But they have a problem. Any small theater company has a problem in that They will do half a dozen productions a year. They might run from 5 days to 10 days or 15 days. But what they're saying is they need a space maybe 50 days out of the year. And yet, if they're going to own the space, they're going to have to pay the rent on it or own it and pay all the costs for it for 365 days a year. So a company in Boston found an answer to that, and that was they managed to convince a developer to give them a theater space which would be used for other things as well as theater. And so the company in Boston set it up as a wedding venue. It was also available for rental as public speaking, if there were rallies, political rallies, things like that. But the theater company had first call on the timing. So that way they had the rent and everything paid. Crows used a section of I think it's called Section 35 of the Development Act within Toronto, that if a developer provides space for a community facility, it could be what's commonly a parquet, something like that, but if they would provide that, the city will allow them to build a bigger building. So Crows and Streetcar Developments got together and said, we'll put a theater inside this apartment building at Dundas and Carlaw. And everybody said, yeah, that's great, wow, and we're going to have weddings in there, and we'll have a patio, and it'll open up to, to well, I'm going to say neighborhood, but just that, they'd be able to spill outside, it'll be fair weather. I mean, wouldn't that be a wonderful thing? And I really think of this as the most interesting part of the story. Technically, I've got some terrific challenges, but imagine, I mean, what a wonderful concept. Well, anyway, technically, it starts to fall down pretty quickly. Imagine a wedding in an apartment building, in a room in an apartment building, and there's patios or space outside where it can spill out outdoors. So we have a room like this, and directly above we have somebody living there, and then we're going to go out on the street at midnight on Saturday night, okay, and party away. Environmentally, from an environmental noise point of view, just does not work. There's no way to solve that problem. It just could not be outdoors unless you happen to be looking at the lake. Mm-hmm. So that part actually didn't happen. Something else I was going to mention is that, I mentioned the speech intelligibility and speech privacy problems or keep noise out of adjacent spaces. So the engineering part of this one is how to keep the noise that would be generated in that room from affecting the condominium suites, which were not only above, but also beside at the upper levels of the room, which is the theater room. So now I've got a fairly long presentation here, but I need to flip ahead to, yes. So this is a plan of the theater. There's a plan of the building. You're only looking at about half of it on the drawing on the left. What you can see is the theater space as a lobby. That's Carlaw going up the west side, Dundas on the bottom there. And as I say, by the time you get to the next level up, you have condominium spaces. So you have both the lobby, a restaurant down here that's shaded, and the theater all directly below residential spaces, which would be condominiums. So the criterion would even be higher than you might have if it was, say, a rental space. Okay. Okay, sorry. Now I have to keep myself on track a little bit here because the slides I've got is 60 or 70 of them, I think, and we only want to deal with about 12 or 15 here. Oh, not even that, 10 or 12. So that's our space. Now if I move on to, where's my count of, Good. So the rest of this talk is about the technical problems that are involved in actually fixing this up so that people don't, the owners above and beside do not hear what's going on in the theater. What do you suppose, and this should be obvious to anybody in the room here, is the biggest problem that the acoustic designer would have here? Very, very simple. We do wonderful acoustic design. Imagine the best acoustic design in the world. And one of our friends here comes along and takes that big gain knob that John was talking about and goes, and all our design work is undone. So the biggest item at the beginning was to make sure that the owner realized that in providing Crow's Theatre, they would have to provide the sound system, and it would have to be limited to some number that we'd agree upon based on what we could design to and how much budget and space there was available. And that number was 97 dBA maximum overall. And if need be, the compressor limiters and whatnot would be kept, say, in the manager's office, so that even when the space was rented out, nobody would be able to override it. Okay? And that's quite a selling job, as a matter of fact. Oops, sorry, yes, so we had 97, and I wound up specifying these are the levels and octave bands that you can have. Because if you're going to exceed that, I can't guarantee that well, I don't guarantee, but anyway, I can't design for it to be below NC20 in the space above. Okay, oops. I'm trying to keep myself on track here. I think oops, there it is. Here's the basic concept for how to separate us from the space above. Up above is the concrete slab of the condo. We've got an airspace, 3 layers of drywall, insulation, and it's on spring hangers, which all looks pretty simple, and we can calculate the requirements for that. The trouble is, also up there, we have a mechanical system, and there isn't space for it below because of the catwalk, so the mechanical system has to come in to the building through the wall, then up through my acoustic ceiling, distribute there back down through my acoustic ceiling in order to distribute through the theater. If that isn't bad enough, we also have loading points for anything that would go on in the theater. We've got catwalks up there, lighting grid, something else in there as well. Anyway, my acoustic ceiling is simply Swiss cheese by the time I finished with it. I think it was something like 35% open area by the time we finished, so it might as well not be there. So dealing with all of that those are all the secondary issues, all sorts of different details to make all of that work so that that ceiling can be fully effective. Okay, now I know we are short on time, so let me move down to, okay, theater wall construction. Okay, oops, it's the next slide, okay. We're looking in plan view here, what would be the theater walls. The building, of course, had concrete walls as part of the construction, fine. A few openings and things we'd have to deal with, but in order to make this work so that, again, the sound wouldn't get through to adjacent spaces and sound wouldn't come into this wall up and short circuit through to the spaces above, we had a 300 gap, a foot gap, and then 3 more layers of drywall. And unfortunately, you can imagine theater people giving up all of that space, weren't very happy about it, but there was just no choice. If we're going to do the noise control, we need this kind of space. Okay, it's a combination of those 3 layers of drywall. You could have maybe 4 layers or 5 layers and a little less space, but one thing or another, you have to have this space. Okay, 17. Okay, another detail about the walls. The walls are exposed to the sound. If they're vibrating and they're connected to the structure, then you have a flanking pass with that vibration, and thus noise can get through into the structure and into the spaces around. So there are special details then for the bottom and top of each of the walls so that they are vibration isolated. So here on the right-hand side, we see the partition track. You can see the word track there. Okay, it's mounted on a flexible pad. It's even screwed down with a bolt with rubber elements underneath the bolt head, so that the vibration induced in that wall by the sound in the room will not get into the structure and around. And similarly, for the ceiling, special detail. Another element of this is just the theater floor. We can't have that kind of construction on the theater floor. I haven't got a foot available. So it was actually a rather complicated and detailed calculation to figure out how much sound we could tolerate in the room that would drive the floor and then go flank through the walls and up to the walls and up to the spaces. And we think we got it right, but it certainly was a question at the time. Okay. 18. Flanking. I got 18 here? Oh, no. So, it's right there. Yeah, I got it. just the concept is simply that the sound in the room causes every surface in the room, including the floor, to vibrate. And if that vibration transfers through to the rest of the building, then it will radiate sound to the rest of the building. And we know it's going to happen, but the question is, can we meet the noise criterion in the spaces? So every part of this construction has to be carefully looked at to make sure that we do not have the flanking paths that would permit that to happen. Okay, and then, let's see, okay. So those are the major issues, but as you go on, yep. Yeah. Oh, I mentioned the theater floor. Oh, sorry, tad confused here. Right. Just some other issues that happened in this building. The washrooms were adjacent to the theater walls, so obviously a special construction, the last thing in the world one wants to hear in the middle of a production is a toilet flushing. And we've, in several cases, had to actually measure that and make sure that it was below the floor by turning everything off middle of the night to get those measurements. Also under this building, there's a parking ramp that goes directly under the theater. So you can just imagine if you had, during a performance, or let's imagine the parking ramp with the usual kind of ribs that are on parking ramps, and imagine a truck going down there. You can imagine a fair bit of noise in the theater. So, in fact, the parking ramp was made particularly smooth and sloped in such a way as to affect the drainage that was required, but without having the ribs that would cause us the noise problem. And then, just rattling on a little bit further, I mentioned the same kind of principles applied to the lobby space, because there could be parties in there. In fact, there's a small studio theater adjacent to it, too, which was not supposed to be used simultaneously, but in fact is, and has exactly the same concern. And then finally, the restaurant that's on the same level. So, just to sum up, now I had a note here, and I can't unfortunately even remember why. I wanted to go to, oh yes, okay, 41. Oh yeah, okay, harking back to that point of the ceiling, which I'm showing here, I just indicate that the ducting for the HVAC has to come in to the room at a lower level, up through the ceiling, across and distributed, and down again, and yet all of that has to be built in such a way that we do not have noise getting into the duct, out of the duct, into the space, and into the room above. And then something was really unusual was that they could not figure out, because of the way this building is, there's only so much space available. There's no rooftop to put equipment. There wasn't much space below it as well. And so actually finding space for the ducting. And so in this case, we actually designed a duct, the S-shaped thing there, into the structure of the building. There is no metal duct that goes through there. We just created the opening in the concrete structure so we could put the air in one side and get it out the other. That's how tight the space is. But again, an example of what I like to call the secondary problems associated with building these things. So, if I could summarize, very interesting absolutely fabulous project from my point of view, in that the nature of the project, Crow's Theatre, and what they were doing and the wonderful productions they'd done, which coincidentally I knew of. I had known Chris Abraham previously through a different connection. I'd been to several productions of his, so it was very exciting to be chosen for the project. And what is really a tremendous technical challenge. And as to whether or not we could actually do any measurements, well, no owner ever wants to go to or the building owner, developer wants to go to a tenant and say, we'd like to come and measure whether or not you can hear down below. Not going to happen. So we just wait for complaints. Well, it opened in January of 2017, and there's never been a complaint from an owner about hearing any noise from the theater. So on that basis, we have to say we did it. Good. Thank you very much.
Thank you, John. I think, given the fact that we've run over a few minutes, maybe we'll just ask Mr. Noonan back to stage for our closing remarks, and then if you have any questions for the panelists, you can ask them after we formally close.
Mr. Noonan, where are you?
Mr. Noonan.
Dr. Noonan.
More
No, he's
questions.
not Dr.
There he is.
There he is. Hi. I have your microphone, Mr. Noonan.
We need some entrance music.
Are we at that time now?
We are at that time.
Fantastic. Anyone? Any
No, we
takers?
deferred questions to after your closing remarks.
Deferred questions until after my closing. Why would you do that?
Since it's already 5:15.
Oh, right. That's a good point by you, Jeff. Thank you.
I have a question for Arthur.
Please.
Do you think restaurant owners are actually beginning to get the message and will acoustically treat their spaces?
Probably a few, but it's a rarity still. It really is. And this client is, I would say, a unicorn in the world of restaurants. But you know, he has such an eclectic taste. He's the owner of probably one of the largest collection of Andy Warhol artwork, and a lot of his restaurants contain that type of stuff. And that's how eclectic this guy is. And you know, little audio issues that we probably would ignore bug him. And it's a crazy world that I'm in, that I have to make him happy, but at the same time, it's like, wow, you really hear this kind of stuff. You know, I'm listening to it critically, I hear it, but you know, the average person doesn't. But he thinks of it as, you know, all the senses are all together and they all work as one to make a great experience. The attention to detail there is just mind-boggling. I gotta say, it's very unusual, and it's a good challenge. I love it.
We're having a municipal discussion, and I think a very good one, about noise in the urban environment, initiated by the mayor. And I was reading, John, you'll recognize the name, a letter to the editor by a fellow named Harold Smith. He's an architect that John and I did a lot of the early Cineplex buildings with. And I thought, well, if he can write into the letter to the editor, I did. I did it from England, actually, a few days ago. And it's explaining to them the Lombard effect. Some of you may know it, some of you may not. But I was writing specifically for restaurant owners. They put in music to soothe, you know, provide a soothing acoustical environment. The Lombard effect is basically humans talk loud enough to be understood above the ambient noise. That is, they talk a little bit louder, which means the next conversation has to talk a little bit louder, and you have a positive feedback loop.
Oh, yeah.
So don't introduce the music in the first place.
Or maybe introduce it in a way that's sort of germane to the audience. How many of us have been in a nice steakhouse or something, and we're listening to music that I would nominally expect my teenage daughters to listen to, and yet as I look about the bar, I see no teenage girls. Anyways.
That's a good thing at your age.
Yeah, there you are. And also, I've now learned that restaurant owners can also be unicorns. See, in my world, unicorns are picture editors. I call them unicorns, but that's important to know that restaurant owners can be unicorns. Gentlemen, thank you.